I know of no major announcements upcoming. Any questions on anything we've done so far?
When is our exam due?
Say it again.
When is our take-home testing?
Okay, we're going to finish the chapter today, so it'll be 1 week from today, technically. If you need more time, you can take it, but just don't still have it when we get ready for the next test. So, because what you're doing then is keeping me from passing it back to everybody else. Get it in as soon as you can. All right. Last time we were talking about, it's kind of boring stuff, I admit, but it's things that you do, applications that involve differential equations. Now, some of these problems you might remember from early in your algebra sequences. You know those famous word problems that everybody loves so dearly. This is one like this. And you had to make a lot of assumptions with that, and you do on these too. But with differential equations, they're generally, once you know how to do differential equations, they're much easier to do. Here's one on mixtures. The mixing of two salt solutions of different concentrations give rise to a first-order differential equation. Okay? And here's what the deal is. Let me see if I can find where they write it out. Let's suppose a large mixing tank initially holds 3,000 gallons of brine, that is water with a certain number of pounds of salt dissolved. Another brine solution is pumped into the large tank at the rate of 3 gallons a minute. The concentration of the salt in the inflow is 2 pounds per gallon, okay? Coming in at 3 gallons per minute. Sorry about my throat. The concentration of salt in the okay, I already read that one. When the solution in the tank is well stirred, it is pumped out at the same rate of the entering solution. Here's the way you set up and work a problem like this. Now, can't get my pen. There we go. Yeah, okay. So we assume the A of t, the pen is really slow, is the amount of salt, okay, measured in pounds in the tank at time t. Amount of salt in the tank at time t. Okay, function of the time t. Here's Curry. Pardon me?
A little slow working out this morning.
Oh, it's a Thursday, isn't it? All right. I'm dragging bottom today too. We helped support a candidate in the Tuesday's primary election. What's that?
You got vote late yesterday?
Yeah, on Tuesday. Yeah, I had to wait till after I got off work because I come in so early, and because we had helped in the campaign, we were invited to the, what they call it, the watch party. Yeah, and so we went, and we were hoping to be over and we could get on home. It was so close. I mean, the election wasn't close. He got right around 50. Second.
Which election are you talking about?
Sorry.
Which primary are you talking
about? It was the Democratic primary in the House District seat, District 54, State House. Okay, and the guy was trouncing both of the components of his opponents, meaning to, he just was getting, but he was right at 50% of the votes. They were down here about 25 each, and most of the night he was at 51, 52 maybe. I think he got up to 53 at some point. So it looked like he was going to do, but it was just too close to call. And with about 81% in, he had more than 51%. So it was okay. And we waited for over an hour. and it never budged off of 81%. When are they going to update this? And when they did update, it dropped to 49. So it went on for the rest, and finally we went home. Huh? Well, we hope not, yeah. But the main thing is getting out the vote. I heard this morning 25% of those eligible to vote voted in the primaries. All the primaries, put together in the state of Alabama. That means, on average, 13% of who voted determined the winner. That's hardly what I consider a democracy, okay? That is I don't know. So we got to get out to vote. The runoff will be okay, but the general election, that's the important thing. It irks me. I really don't care who you vote for. I want you to vote, okay? That's part of the deal, okay? To me, if you don't vote, you lose the right to gripe. Don't even say a word. If you didn't vote, don't say a word, no matter how bad it is. Sorry.
I think that more people would vote if they did that.
Yeah.
For sure.
Yeah, I think so. I sure hope so. All right. My wife said, why don't people vote? I don't know. Okay. So here's the problem. We're talking about mixing problems. You got one solution of brine coming into a tank. It contains another solution of brine. And then we haven't gotten to the part where some of it is going out. Okay? So if A of T is the amount of salt in the tank at some time T, then the rate at which the amount changes, that's your differential equation. When you see the term rate, especially when it's a function of time, dA dt is the rate of change. Okay? The rate of change. This is rate of change in salt. And there's a real simple relationship here. The rate of change in the salt is the rate of change of that coming in minus the rate of change of that going out. Now, for the life of me, I can't see in the problem where they indicated. The picture shows that. Oh, okay. Oh, no. Okay, I see it now. It is pumped when the tank is well stirred. It is pumped out at the same rate as the entering solution. Okay? But the original solution was different, and that's the key here. Okay? Rod, right? Okay. All right, good deal. Okay. So, since it's going out at the same rate, the flow is the same rate, but the rate of salt is different. So and this is the amount of salt. So dA dt is equal to input rate of salt minus the output rate of salt. Okay, now the input rate we know. They gave us in the problem. They said the brine solution is pumped into a large tank at 3 gallons per minute. The concentration of that in the inflow is 2 pounds per gallon. So 2 pounds per gallon times 2 gallons per minute, 3 gallons per minute would be 6 gallons per minute. So dA dt is equal to 6 gallons per minute. That's how much salt is coming in that inflow. Okay? Now what's the outflow rate? The outflow rate, it says it's going out at the same rate. Okay? And that's going out at 3 gallons per minute. Well, how much salt is in that? A, because that's your mix. Okay? That's how much salt is in the tank. So, what's flowing out is, I'm sorry, why did I write a D? Is A, that's the amount of salt, okay, divided by, where is it? It's pumped out at the same rate as the entering solution. So the output rate of the salt is 3 gallons per minute times A, okay? Okay, A of T. Now that's not quite right because there's something missing here. That's it's the concentration that's in there. So it's A divided by, sorry, yeah, that's what's wrong. You have a total of 300 gallons. That's constant in the problem. So the amount of salt divided by 300, this is pounds of salt per gallon, okay, times gallons per minute, and that's the change of salt per minute, which is what this does, and that, I'm sorry, this is pounds, not gallons, sorry. That's part of what was messing me up. Okay, this is pounds per minute. Okay. It would have helped if I just spelled things out, but I was running out of room. Where did that 6 come from? It was 3 gallons per minute coming in times 2 pounds per gallon. That was the concentration coming in. So you see the gallons go out, and that's 6 pounds per minute coming in, 3 gallons per minute going out. That's the solution. This is the pounds of salt out of the 300 gallons that's in the tank. So that's the gallons here. So this is going to be pounds per gallon. So everything works out okay then. The gallons will cancel out, and you wind up with pounds per minute. And there's your differential equation. Now, what you're looking for is what is did they indicate what you're looking for? Well, it depends on what you're looking for, I guess. And one type of a problem, you could have what is the concentration of the output. I don't think they indicated what you're looking for now. That could certainly be the thing. What's the concentration in the tank at any time t? That could be the thing. You could have a variety of answers there. Okay? But your differential equation is rewritten just slightly here. dA dt, and there's a reason they rewrite it this way. 3 will go into 300 100 times, so this will be, move that to the other side, plus 1 over 100 A of t, and leave this on this side is equal to 6. Okay? Later we'll see why they wrote it this way. This is one way to do a linear differential equation. This is sort of the standard way to set it up. And by the way, is this a linear differential equation? Yes, it is. That's to the first power, that's to the first power. Okay? Okay. Probably more time than that was worth. And here's another potential paper topic here too. When you're draining a tank, Torricelli's law, good Irish name, no, I'm sorry, Italian name, he determined that here's a differential equation, the rate at which something is leaving a tank is proportional to the rate at which a tank is emptying depends on the pressure that's in the tank. That's going to determine the rate out. And of course, if it's a huge tank, lots of pressure in it, you open up the valve, it's going to come spewing out, right? But then as the tank drops, it'll slow. So you have a changing outflow. And torus, when you have something changing, differential equation, okay? I won't go into gory detail on this one as well, but from physics, a falling object, the velocity is the square root of 2gh. I don't know if you had that in physics yet, but you'll run into that. And so your change of volume, here's your differential equation, the rate at which the water is coming out in cubic feet per minute, say, that's a common U.S. customary. Cubic meters per minute would be perhaps in the SI system. So they should use seconds, but that would be, well, that would work too. Cubic meters per second would be all right. That would be minus a sub h. Now, I have to define that for you. That is the area of the hole, okay, at the bottom, and they're giving it in square feet, which is a huge unit for that, times the square root of 2gh, okay? Now, let's see if that makes sense. Area is measured in square feet. Velocity is measured in feet per second. That would be cubic feet per second, and this is cubic feet per second. So yeah, that makes sense. Except I think it's in, yeah, cubic feet per second, okay? I was saying CFM, cubic feet per minute, but they're doing cubic feet per second. All right? They can adjust this slightly, and this is where Torricelli's law comes into play. Let's see if we can. Okay. If you have the tank here, okay, with a little hole down here, and this is your area of the hole, is that determines a lot, okay? You also have the area of the tank. So I want to call that T. They called it W for water. I don't know why. I prefer, well, no. T wouldn't be good because you're using T for time. So I guess that is better to call it W. The area of the fluid or water or whatever it is, okay? You can also say that this area times this height, okay? But that height is a function of time because it's the water level height, okay? Not the height of the tank. It may start full, but it's going, the water level height would be h of t because that's going to decrease in time, okay? So then we can, the amount of water, the cubic feet of water would be the area times the height, right? Because that's the volume of water above, and that's what your V is. So the V is equal to A times H, but H is a function of time, so V is a function of time, and that's why you can take a derivative of it. So if you include that in the problem, where this is A sub W, this would be A sub W, that's a constant. The area, as long as it's a cylindrical tank. It's not the peach down at Chilton County, Clanton, okay? It's not that tank. This is a cylindrical tank, okay? And that would be dV dt would then be, if this is V, A is a constant area, and then it would be dH of t dt, and that's equal to minus A of the whole, the area of the whole, times the square root of 2gh. And notice here, we have an h over here and the h there. That h is also a variable, okay? Variable height, okay? And then we can divide both sides by a sub w. You have dh, oh, sorry, I don't need that one in there. Too many parentheses get in the way. dH dt, I left off the other one too, is equal to minus area of the hole over the area of the tank, nice ratio there, times the square root of 2g, that's also a constant. That could be included with that one, times the square root of h, because that's your variable, okay? And actually, I don't need another set of equal signs there. That is your equation, okay? Now, tell me what kind of equation that is. Well, height, ordinary, order, first order. Say again. So your variable here is h. This is to the first power, that's to the 1/2 power. It can't be linear unless all these are to the first power. So that's non-linear.
Is that a L or an H?
What's that?
Is that a L or an H?
That's that's an h for height. That's the height of it.
I thought it was an L.
Oh, I see. Okay. Making fun of my writing. I got it. I'm not hurt, but I remember that on your no, I'm just kidding. I'm just kidding. Okay. All right. So there, another differential equation. Now, of course, you know, you can have initial conditions. What if the tank started with a height of 10 feet? So h of t would equal to 10 or something like that. Easily then to see that you had a boundary value problem there. I mean, an initial value problem there. Lawrence here. All right. So missing Monica and Jasmine. All right. Now, anyone done your physics yet? Or y'all still got that to go? You have done. Okay, had the E&M, electricity and magnetism?
Oh, no, that's physics 2.
Huh? That's physics 2. Okay, yeah. Physics 1, mechanics. Physics 2 is usually electricity and magnetism. There's other things in both of them. When you get there, you'll run into this as well. Okay? We're going to talk about a certain type of circuit. Okay? Series circuit, where you have a voltage supply here. They don't use the same symbology I'm used to doing. Usually the symbol for this is like a turbine, okay, meaning it's alternating current. It's alternating current, that's your voltage supply, and that's a function of time. E is a function of time, where E sort of stands for EMF, electromotive force, except it's not a force. You know, they don't use that term anymore, but they still use the E and call it EMF, but they don't call it electromotive force. And this is going through an inductor, okay? And it's also going through a resistance, okay? So this is an inductor with symbol L, resistor with symbol R, and then finally going through a capacitor, symbol C, okay? Resistance is the constant of that resistor. L is the inductance of the coil, the inductor, and C is the capacitance of the capacitor. Okay, so they use, except for the L, okay, and here's Monica. We're just missing Jasmine again, okay? Now, the voltage is a power of time. That is a function of time. Okay? Now, this is what supplies the voltage. You have the voltage drop across each element. And the voltage drop has to equal the initial voltage put in, which is a function of time. Now, if these weren't in there, inductors or capacitors, that's a linear relationship because E is equal to IR. Okay. Introducing the next thing, the current. Oh, don't use this pen on the screen. Duh. Here's the current, I. Okay? and I just arbitrarily put it in that direction. Alternating current doesn't really have a direction, but just pick a direction, and we'll go through that. Okay? Now, so voltage depends on current times resistance, and it also has the voltage drop across the others have. And by the way, this book uses little I. I usually use capital I, so to keep it constant. To keep it uniform, I'll put a little I here. And there is a reason for that too, okay? Usually the capital I is for direct current systems where the current is usually constant. This I is also a variable because it changes with time. Of course it does. As your voltage is changing, the current's changing, okay? And this is probably 60 cycle or something like that. So it's definitely a function of time as well. Now, L is a constant, R is a constant, and C is a constant. Okay? But when you start messing with these, and this will be if y'all haven't had the physics yet, let me tell you, I is also equal to the time rate of change of your charge. Okay, and there's a reason I have that. So this is dq dt. That itself is a derivative. The current is. Now, the reason I say that is the capacitance depends on charge, not current. Because guess what? There's no current that crosses that capacitor. There's charge that builds up on the capacitor. That's what capacitors do. They build up charge. Current goes through the resistor and into the inductor, but the charge is what builds up on the capacitor. So that's why we need to introduce the charge. So this is sure looking like it's going to be a second order differential equation, and certainly it is. Okay? Now, you aren't supposed to know the physics here, but let me give it to you. The inductor, measured by the inductance, by the way, the unit for that is henries, okay? Now, they put that as a little h, and that's not very nice, because it was named after a guy named Henry, and any unit that's named after a person usually is capitalized, okay? So that should be an h. I'm not going to put a little h down there for henries, okay? And here's what your the voltage drop across an inductor is L times di dt, the time rate of change of the current. Because remember, current is a function of time. So there we have a derivative there. Okay? The resistor is just EI. Okay? The voltage times the current. Okay? I'm sorry. It's the voltage drop is what that's true. The resistance is voltage, and it's not. It's divided by, so sorry about that. The resistance, I was trying to give you Ohm's law, and I gave it wrong. E is equal to IR. That's Ohm's law. So, the voltage drop is the current times the resistance. I'm sorry. I keep putting capital I's. Current times resistor. So this is the voltage drop. This is the delta E across an inductor. This is the delta E across the resistor. Now, your capacitor is not dependent on current. It's dependent on charge. And that is the voltage drop E, the delta E for a capacitor. Let me put for resistor, for inductor, and this will be capacitor. I shouldn't use I. Let's use L. Okay. For that voltage drop is 1 over C times Q. Okay. That's the voltage drop across the capacitor. It only works in alternating currents. Capacitors just shut down a direct current. Nothing flows. But alternating current, since your current is always changing, your charge is always changing, then your capacitance is a resistance. It's not other resistance. It's called an impedance. Okay. So with those in mind, and the fact that I is dq dt, your total voltage drop in the system, which will be the total voltage supplied by the system, is equal to, now this, remember, I is a function of Q, is the first derivative of that, so this turns out to be L times d2q dt squared, because you take derivative of the derivative, okay, plus dq dt, remember I is dq dt times R, plus just 1 over C times Q. There's your differential equation. What can you tell me about this one? It's a ordinary, what you say, linear, certainly is, and second order, because it's in the second derivative of Q. And there's your differential equation. Now, if you remember back, you've had your Physics 1, which certainly included Newton's laws and Galileo and the whole works there. You know that one expression for the fall of an object off of a building, let me go on and clear this so you won't get these confused. These are all just examples of where in real life you're going to see differential equations come up. Okay? Now, as engineers, you're going to try to avoid them like crazy, right? You're going to try to get tables and other things to give them to you, but this is where they come from. Okay? We know from Newton's second law that the net force acting on an object is equal to your mass times your acceleration of the object, right? Okay? Now, at a falling object, okay, a falling object, the net force acting on it will assume no air resistance to begin with. Net force acting on it is the weight, and that's all, okay? So this will be your mg, okay? And this is equal to m, and what is acceleration in terms of velocity? dv dt, differential equation. But in terms of displacement, that would be what? d2s, we'll call it, or do they call it h? Yeah, they call it s. d2s dt squared. So that's what your mg is. But guess what, folks? Oh, and by the way, that is a minus sign because the net force is always downward. Okay, so that's why the minus sign. Guess what? This is what Galileo contradicted the expert Aristotle. Of course, they were separated by several, at least one and maybe 2 millennia, so it was a direct thing. The acceleration due to gravity is that acceleration of your falling object. Okay? So this basically is your differential equation. d2s over dt squared is equal to minus g. Just a constant. An ordinary, second order, linear differential equation. And usually we know s of 0, in other words, how far up the Leaning Tower of Pisa you were when you dropped the rock, if you were Galileo, if that was indeed true. That was your initial displacement. And if you drop the rock, then your initial velocity, which is your second derivative, which will be v at 0, which is s prime at 0, would be s0. I mean, v0. Yeah, v0. Okay, now, if you drop the rock, that's going to be 0 because you're not giving it initial velocity. If you just released it from rest, that V0 is 0. However, you could have thrown the rock, right? And that would give it to you, okay? If you threw it downward, that would be a positive V0. However, you could have thrown it upward, and then this equation still works, okay? That would be a positive V0 then. Still would work, okay? Now, if you were to, when you, and they haven't shown us how to do this yet, but you know it from physics, hopefully, whoops, that your S of t, displacement at any time t, after you, however you release the rock, threw it or dropped it or whatever, this is equal to negative 1/2 gt squared. That's from integrating this thing once, you get a gt, twice you get a 1/2 gt, but you always have the minus sign, okay? Plus v0 t. Now, of course, if the v0 was negative, then that's going to be a minus number there, but it's just whatever that was. And the naught didn't close, did it? Plus S0. And there's your most general form of, first it was Galileo's equation, I guess you would call it, and then you would then attribute some of it to Newton as well. Now, what was our assumption there? Anyone remember? I sort of spewed it out there pretty quickly. No air resistance. If you are doing air resistance, there's another force on it besides the force due to gravity, and that would be the force due to air resistance, which depends on velocity and surface area and other things like that. So then you would have, this equation would have a plus, and then it would have a dv dt, ds dt, because that's what velocity is, with some other things in front of it. So you could come up with some pretty hairy differential equations. This is the simplest one, okay? But differential equations will take care of all of them. So this is from Newton's first law of motion, which basically was developed by Galileo, and his second law of motion. So any of those folks are good paper topics as well. Okay? Oh, and here's Galileo. He's mentioned next. Falling bodies and air resistance. Here it is. I didn't know they were going to do this next. Here would be your differential equation then. Another way to write your acceleration is dv dt, right? So here's the mass times the dv dt is equal to mg minus kv. Okay? Now, what's a little different about this, they've switched the signs around on you without really telling you why and how. But as your velocity is increasing, this net force is increasing upward, okay? And basically, well, it's just not real clear of why they did that, but there is your differential equation there. And this is then called, the K is called the it's a constant, proportionality constant, that's the name word I was trying to think of, and it's also may be called the viscous constant, because that term is your viscous damping. The denser the fluid, and by the way, air is a fluid, gases and liquids are fluids, they come by way of that. Now, if you then got this V back down to S's, then this would be M times D2S dt squared, just like we did before, is equal to and they just are leaving this as mg, and this would then be minus k ds dt, because your velocity is time rate of change of displacement. Okay? And then you could rearrange that and have m d2s dt squared plus k ds dt, and then they put equal mg. Okay, no reason not to bring them all to the same side, but they did. Okay, now this is your net force. This is the gravitational force. That's your viscous damping, which is your air resistance, basically. Air resistance up. Well, now your directions are reversed. Your air resistance is up, your acceleration due to gravity is down, but if you move them to the same side, they have opposite signs. So the sum total of this has to equal that. Okay? So that's what we're talking about. You'll never have this be greater than that. I mean, it can't happen. At best, because this goes to zero. That's when the air resistance is equal to the force. And that's what you call your terminal velocity when that happens. Okay. That's probably more than you wanted to hear. Okay. Yeah, they have so many of these. Suspended cables. Okay. This is whether you have a suspension bridge like Golden Gate or many other bridges are like that, or telephone wires. Have you just noticed that telephone wires always have a dip in them? Why don't they pull those things tight? They could certainly save money on wire, couldn't they? Why have extra wire there that's just hanging there? The answer is, number one, you can't. Gravity is always going to pull it down. Even if you got it as tight as you think you can get it, if you were to actually measure, there is a sag in the middle. Okay, gravity is always pulling down. This is a tensile force this way. It can't overcome gravity. So there's always going to be a dip. Okay? Now, if you were to go out there in the wintertime stringing these, in the middle of summer, stringing these cables and say, look, I want to get them as tight as possible. I want to save as much as I can on the wires. It's going to save on our budget here. So in the middle of summer, you're stringing these wires, put them just as tight as you can get them. Sure, there's a little sag there. What's going to happen when it turns winter? You're going to pop the poles. Believe it or not, you will break the telephone poles, or you'll break the cable one. Okay? Because in the winter, because coefficient of linear expansion, when you heat a metal, or it's the other way, when you cool the metal, it's going to shrink. And if you got it as tight as you can in the summer, when it gets winter, it's going to pull those together. So either the wire breaks or the pole snaps. And believe it or not, the pole often snaps, if you were to do that. It's amazing the amount of strength, energy that's in that. So there's a diagram here in your book, and basically I'm going to move ahead here because this one's a little tougher to talk about. But here's your differential equation. Let me get I still have to get the illustration in there, but it winds up dy dx, okay, is equal to W over T. Now, W is the weight of the wire that gravity is pulling down on, with that is the force due to gravity. T is the tension you put in it to begin with. And the tension is, the problem with it, the tension has two components. W is always down. The tension is usually like this. It's whatever direction, whatever your sag is, it would vary like that. So it would have a horizontal component and a vertical component. So you would have to set up this, and we're not getting into that, but you would have to set it up in both dimensions, okay? and you would have to use vectors on it. Now, all that, and I don't know if that was really all that necessary, but it says, what lies ahead? Does the differential equation actually have solutions? We don't know, okay? We really don't. Remember, there's the existence and the uniqueness, so we have to determine that. Can we somehow approximate the values of an unknown solution? Yeah, that's what numerical integration or differentiation is all about. And in real life, you're probably going to wind up doing more numerical than analytical. Okay? So what we've been doing and what we will do is largely analytical. Okay? There is qualitative, which just is, and we'll do a little bit of this, but not too much, just get a general feel for what's happening. And then there's numerical, where you're approximating it using finite difference or finite sums. Okay, so those are all different approaches. Now, the remarks are always a bit deep, but I did want to point out some of the terms here. In this section, we've done a lot of different applications of differential equations where you might be using those. Each of those samples, I think, they say here, is what they call a dynamical system. Things are changing. That's why you have derivatives. That's what derivatives do for you. They deal with change. Okay? That's where differential equations come into play. In more precise terms, a dynamical system consists of a set of time-dependent variables. That's what I said. It's about all your rates. Now, this one is not a time rate. This is a change of y with change of x. So this one is sort of the one exception of that. Okay? But most of the others were changes with time. Okay? So they consist of a set of time-dependent variables. Those are often called the state variables. We're not going to really get bogged down in that, but you might in your engineering courses. The state of a system at time t then would usually set your initial condition, or sometimes a boundary condition. Okay? The solution to the initial value problem, if you have initial condition, will be the response of the system. What has the system done at some other time, rather than your initial time? So they do say, one last point, not every system studied in the text is a dynamical system. We'll examine some static systems in which the model is a differential equation. So you'll have a variety of those. Homework exercises here, population dynamics, think through, maybe play around with either 1 or 3. So answers to the odd number problems are in the back of your book. I can't swear all these will be here, but you can look and see which ones are before you worry with them too much. Newton's law of cooling is number 5. Spread of disease or technology. That's sort of spread of the disease or technology. I think what that means, spread of a disease or, say, a technological virus. This will follow the same pattern. That is number 7. But maybe the spread of technology would follow that same pattern. Mixtures are either 9 or 11. Draining a tank would be 13. Your electrical examples is 15. Falling bodies and air resistance, 17. Newton's second law and Archimedes' principle, that's only an even problem. We didn't really do that, but it shows you that. There's another potential paper topic. Archimedes, okay, or his principle, okay. Newton's second law and Hooke's law, there's another potential paper topic. That's number 19. Second law of variable mass, okay. What would be a variable mass? I thought mass was constant. What if you're launching a rocket? Initially, that thing weighs tons, okay? And when you launch it, you're burning fuel like crazy, so you're losing mass, because that fuel, once it burns and the exhaust goes out, it's no longer part of the load. Okay, and then when you get a certain height, they eject the first stage to get rid of some more weight. So that's a variable mass or variable weight. And we didn't do one like that in class, but 21 is like that. Law of universal gravitation. Excuse me. We didn't do one like that either, but they give you enough to go on. That's number 23. And then there's additional mathematical models. If you want to look at that, you can do so. Some of these are pretty important. Infusion of a drug, what's your rate? What is the amount of drug you have in your body at any time? They can give you an infusion, and then in time, that passes out of the body. There's a bunch of interesting stuff here. I know the discussion problems are not in the back. I think some of the other models are, like 25 or 27, probably are, possibly 29. I would think so. But the others beyond that, probably not. Okay? That finishes chapter 1. Okay? This is when I would be giving you your test. But I already gave all of you a test, right? All of you got it, right? Okay. Now, notice in your test, a lot of these are verified. We haven't figured out how to solve a differential equation yet. So right now, all you're doing is showing this solution fits that equation. So it's going to be a fair amount of writing. Be sure you write down enough to do. Don't just say, yes, this equals that. Well, no, that was given in the problem. Show me that you know how to do that. Other problems that might be helpful to you, and the odd number exercises are here too. Any of the odds, number 1, number 3. This is chapter 1 in review, pages 34, 35. 3, 5, any of the odds 7 through 11, 13, 15, any of the odds, 15, and then any of the odds 17 through 21, either 23 or 25 or both, 27 or 29 or both, 31, 33 or both, and 35 or 37 or both, and 39. Okay. So y'all got your tests. The only one who didn't was Jasmine. She's still not here. Okay. Now, let's move on to chapter 2. Any questions on chapter 1? Did you look at your test? Any questions on that? Did you have a question? Okay. Technically, they're due 1 week from today because this is when we finish the chapter. Okay. If you need more time, you can have it. But Okay. Wait just a second. Let me get my copy of it so I can know what you're talking about. Say again. Yeah. No. All that is take that through. That's all it is. Pretty easy gimme problem, right? Number what? 2. Yeah, I got it. What was your question?
Basically, the first 2 parts from that third, we use those just to drop the C's.
Oh, you mean the third part then? Okay. Okay. Yeah. Okay. I think this is what I understand the thing to be. Your y prime and y double prime, and I'll confess, you don't have room to put them all on that little line, okay? Probably going to need on the back of the page, scratch work or something like that, because these get a lot hairier than I thought they would, okay? But yeah, the C1 and C2 will show up in both of those, okay? Certainly they have potential to. However, the third part, is this what you're asking? Yeah, the third part then is express some function F of y prime, and y triple prime alone. Okay? And that, yeah, and it says, and then combine these derivatives as a linear second order differential equation free of the simple C1 and C2. In other words, they will be eliminated. Is that what you were saying?
Yeah, just making sure it's.
Yeah, that's what it's meaning. And if you'll go back, let me mark my page here. This is boy. This is kind of like what we were doing. This is only, I think, maybe the second or third time I've taught from this book. I have been through so many differential equations books. Okay. I think they first introduced this capital F back in section 1.1, but then it carries over there too, so it doesn't show you exactly how to do it, but it's maybe not on that page, but yeah, you manipulate them and get them so that you eliminate the C's. That's basically your procedure with that. Okay, and you'll see some examples in the book. I just can't lay my eyes on them right now. Okay. I don't think it's the. I think it's in that first section, because the last section certainly doesn't have it, and the IVPs don't really address that too directly. So I think it's all in that first section. So let me see. Well, okay. On page 14, it's almost like it. Yeah, number in the upper 50s there, you get into doing some of the problems like that, especially if you find one that has the answer in the back that might help you step back through it. But once you do it, I think you'll see that there's some fairly easy ways to get those to divide out or add or subtract out, that you just are able to leave. Yeah, so that's what you do. Get rid of the C's. Okay? Any others? Sure sounds like it should work, shouldn't it? Yeah. Really easy problem. Sorry about that. Yeah. Too easy. That's exactly it. Okay. What's that? Yeah. And this was a pretty simple chapter, but I tried before to combine chapters 1 and 2. 2's a really long chapter. I thought that doesn't give you your first test till way later in the term, so I just threw in a really. What's that? Yeah, it gives you a grade a little earlier. What did you say? I can't hear. Yeah, it just takes too long into it. So I said, let me go and give you a test early, and then the next one will be plenty. I didn't even need anything in chapter 1 by the time we finished chapter 2. So I said we probably need to be tested on that. So, yeah. So this is sort of a get your feet wet one, okay? The next ones will have a lot more to do in them than this one. Okay? So, enjoy. Chapter 2 is first order differential equations. Okay? No second orders, but we'll have a variety of ones. In fact, there's 6 sections here, whereas there are only 3 in chapter 1. We're going to look at solution curves, and this is kind of, you remember that little blurb we had at the end under remarks in 1.3 when it said, oh no, right at the end of 1.3, it says qualitative. Section 1, 2.1 is very qualitative, okay? Not precise at all, but it just gives you an idea. Then sections 2, 3, 4, and 5 pretty much give you the basic techniques, almost in the order you will approach them for solving first order differential equations. This will cover just about all of them I think you'll ever need. But if you can't, if none of these work, then 2.6 gives you a numerical method for when you get those that you just can't figure out any other way to do it, or you just want to skip right to the chase and do numerical. Okay? So let's start with solution curves. I'm so sorry we're not getting anything to me that's all that concrete yet. First chapter was sort of esoteric, get a feel good about it, and even 2.1 is just a good feeling about it. Now, first order differential equation basically is going to look something like this, isn't it? dy dx, there's your derivative, is equal to some function of x and y. Okay? It's about all you can do with the first order differential equation. Okay? Now, that function of x and y, if it's a function for any x or y you put in there, you get one and only one solution, right? That's what makes it a function. Okay? Now, if you can imagine plotting that function on the good old xy plane. Okay? Okay? Now, xy plane is made up of, I don't draw these too evenly. This point right here would be, sorry, that was ugly. That point right there has some value, x1, y1. Okay? Right there. It has coordinates, x1, y1. That looks to be close to 3, 3. Okay? Whatever it is, that has some value. Well, you could plug that value in your function, right? And you'll get an answer. And what does that answer represent? That question on the test he was just asking about, number 5. dy dx represent? The slope. So if you knew the value of x1 and y1, plug it in, f, and guess what you get? You get the slope. If that slope was a plus 1, that function's going like that. If it's a minus 1, it's going something like that. So you got a slope. You know where this thing is heading. If it's constant, it's going like that. So if you do this for every point on the xy plane, you get a mapping of arrows, okay? And they will change direction, stuff like this. And you can almost, if you get a dense enough array of them, you can almost pick out any family of curves that you want to have. And remember, that's what we were seeing in chapter 1. A differential equation, ordinary differential equation with out initial value. It has a whole family of curves, a whole bunch of them, okay? And this will give it to you. So that's what we're doing here, is basically looking at that. The derivative dy dx of a differential equation, y is equal to y of x, gives slopes of tangent lines at every point on the graph, okay? As long as you don't have 0 in the denominator, okay? Then it wouldn't, okay? So you can talk about that function as being f of xy as being the slope function, because that's what it's describing. Or, just like we saw in the last, those examples, the slope represents a rate. Time rate of change, distance rate of change, whatever is some sort of rate, the dependent variable per independent variable, dy dx, or dy dt, dx dt. Okay. Now, each little piece there, you know the curve, that f of xy, a lot of times is going to be a curve. What the slope tells you is just what direction that curve's going. So that's a linear approximation of that. And like I said, if you get them close enough together, you can almost map out exactly or fairly close to where they're going, qualitatively. Okay? Now, we call that collection the slope field when you have a whole bunch of these, or direction field. Okay? And example 1 is going to deal with this. And what I think I'm going to do here is use this graph. Now, this is way too small of a graph for what they've got in the text, but let's give it a shot. The direction field for the differential equation dy dx is equal to 0.2 xy. dy dx is equal to 0.2 xy. Okay? Now, let's just, actually, this graph is fine for what they're doing. You give me some points. Pick a point, any point on this grid. This is a 1, 2, 3, 4, 5, 6, 7 by 1, 2, 3, 4, 5, 6, 7 by 7 grid. Now on my screen, this looks sort of rectangular. This looks a lot more square. So it's because my screen is stretched this way. So that's much more square. Pick a point, any point. Give me a point. 1, 1. Okay? So the slope at the point 1, 1 would be what? Point 2. Here's a point 1, 1. The slope there is 0.2. Let me just estimate it like that. That may be a bit too much. It maybe should be flatter than that. Give me another point. 2, 2. What will that slope be? Point 8. Okay, almost 1, right? I hope I did that. Okay, give me another point. 3, 3. What would that give you? 1.8. So that's the slope of almost 2. Okay. Next. 4, 4. Y'all staying on that, aren't you? Okay. What would that give you? 3.2. Even steeper than before. Whoops. Did I hit the right? Yeah. 4, 4. Okay. No, I missed it, didn't I? I went up too far. I did 4, 5. Okay. Next. 2nd. 1, 2. Buckle my shoe. Okay, what's that? 1, 2 would be up here. What's its slope? 0.4. Okay, so that's less than a half. Okay. 2, 1. That would be 2 here, 1 there. That would also be about the same slope, right? Exactly the same slope. Any others? 2nd? 2, 3. What would that be? Here's 2, there's 3. What would that be? 1.2. I can't get it to write. A little bit more than 1, and that's probably not very accurate. But you get the general idea. Y'all are way too hard of workers. Okay? I want to do some real easy ones. 0, 0. 0, 0, 1. Or 1, 0. 0. 2, 0. 3, 0. 4, 0. 5, 0. See, I get a lot more done than y'all do. Okay, 6, 0. 7, 0. Okay? Or 0, 1. 0, 2. 0, 3. 0, 4. See, if you're multiplying by 0, it doesn't matter. These are all going to be zeros. Okay? And negative 1, 0. Negative 2, 0. Negative 3, 0. Negative 4, 0. Negative 5, 0. Negative 6, 0. Negative 7, 0. 0, negative 1. 0, negative 2. 0, negative 3. 0, negative 4. Okay. I got the easy ones done, right? Okay. I was really lazy. Okay. And if you look in the book, you see what's happening here. So let's go back to the second quadrant. Go on over to the second quadrant. Give me a few of those. Second. Okay. Negative 1, 1. Okay, that's this point. Okay. And what would that be? Negative 0.2. Okay. Slightly negative. Okay. And this would be a little more negative up here if you did negative 1, 2. That would be a little more negative, and then a little more negative. Yeah, after a while you get the idea. How about negative 2, 1? About the same as that one over there, right? Okay. And then that would be about the same as the next one. Okay. And you keep on going that way. Okay. And these will be going down like that. Let's go to quadrant 3. Okay. What would that give you? Positive 0.2. So here we have one a lot like this one here, just like that. Over here, it'll be negative again, right? And, you can back off and you start seeing patterns here, and you ultimately get to where you are in the book. It can take a long time to do a whole grid, even a small grid like this. But after a while, you get and what I like to call these are your streamlines. Okay? This gives you the idea of where it's going. Okay? Where the function's going there. So obviously, it's going to stay horizontal here, and it's going to be coming down here, going up there, coming up here, and going down here. And you get the idea that indeed you have, if you were to classify those are hyperbole. And that's exactly what you get when you get a cross term like that. Something is dependent on the other to the 1 over power. They're inversely proportional to each other. Okay? So, in your text, you have, I'm going to try to match their colors, because not everybody has books yet. Here is ooh, that's supposed to be red. Okay, there we go. There's that value there. And back earlier, when we actually did this, your parameter, I guess they do that. So let me find that in here too. Oh, here it is. Go back to black. Your actual solution that we did much earlier, example 1 of section 1.1, here was your solution. Y is equal to, I just had it, and now I've lost it, e to the 0.1, okay, y is equal to ce to the 0.1 x squared. Ce to the 0.1 x squared. There is your differential equation. And if you had c is equal to 0, that corresponds to y is equal to 0. That's that line right there. So there's your c equals 0. So this sort of helps define what those C's were, you know, or help you at least see. This is C equal to 0, okay? Not much of an equation, constant equation, not much of an exponential there, but it's the case. Now, there's a bunch of other curves that basically do this, and then do this, and then do this, and do this, and do this, and do this, okay? These are your C's greater than 0, okay? Now, why would they be C's greater than 0? Well, a couple things. First, this is an even function. Same thing on either side of the x-axis, y-axis, okay? So if it's going up there, it's going, well, E is always positive, okay? If C is positive, this is always going to be up there somewhere, okay? And then you got the x squared, okay? But if C is negative, your E is always positive because you know, no way around it. So with C is negative, you get the streamlines down here. Let's do green. I didn't draw enough to do these, but you know, you get like this, and like this, and like this, and like this. And they should be symmetric about the y-axis. I got a little off there. But there are certain pairs of these that are opposite each other, so that indeed forms what we call hyperbole. Okay? So they're not classifying them there. So down here, your C's will be negative. Oops. C less than 0. Those will be your negative C's. Because otherwise, the exponential will never be negative. But if you put a negative constant in front, then that flips it over. See how that works? You can't do them exactly, but you get a qualitative idea of what's going on. Okay? Let's do example 2. Use a direction field to sketch an approximate solution curve. Again, these are approximate, so they're qualitative. Solution curve for the initial value problem, dy dx equals sine y, right? Yeah. Initial value being y of 0 is equal to negative 3/2. Okay. They have you pause before they say, before proceeding, recall that from the continuity of f of x, y equals sine y, and the fact that the partial of f with respect to y is cosine y. There's a theorem way back in chapter 1 that we did that guaranteed the existence of a unique solution curve passing through the point x0, y0, which in our case would be 0, negative 3/2. Okay? So let's start here and pick a few values. Okay? So you pick some. Notice there's no x's to pick, are there? So let's just do sine y. How would that look? Y is equal to 0. Your slope is 0 everywhere. So well, that looks sort of familiar. Okay, we saw this in the last one too. No matter what the x is, when y is 0, because sine of 0 is 0, that's that everywhere. Okay. Pick another y. Huh?
Y is pi over 2.
Pi over 2. Okay? At pi over 2, that's, okay, pi, let's do pi first, okay? That's 3.14. 1, 2, 3. Let's do it up here. And what is the slope of that? 1. Okay? I'm approximating 3.14 and trying to get these to be a slope of 1, right? Am I doing a decent job? Probably not, but. What's that? Oh, wait. Sine of pi is 0. Sorry. You're right. I was still thinking pi halves. Ew. Let's just erase these. Sine of pi would be 0 again. So let's go back and put these. See, I was lazy picking the easiest one again. These are all zeros again. Okay? Every one of those is a 0. 3.14, blah, 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 blah. Okay? And negative 3.14. Okay. You get the general idea. I'm real tempted just to draw a horizontal line through that because it's going to be everywhere. So why don't I do that? Okay. And 6.2. That's about 6.25. That would be about here. So these are all going to be horizontal. And this one up here. Ooh, I can't draw horizontal lines. I sure can't draw horizontal lines too well. Okay, all those are horizontal. Now let's do the pi halves. That was about 1.57, so that's just over 1.5 here, and that's your slope of 1, right? So there are some ways to sort of speed the process a little way, you know. Okay, but what do we have at 3/2 pi? Sine of 3/2 pi. Anybody? Huh? 3/2 pi. Second? -1. Those will all be -1. That's somewhere about here, isn't it? 3/2 pi. 3 times. Yeah, so it's about 4.5, right? Okay, about 4.5. 3, 4. A little bit more than that, so this will be a -1, right? So these are going down like this. Every one of them, okay? I'm taking way too much time doing this, but I'm not even writing my arrows on them anymore. Down here, these would be down again. This would be negative pi halves, would be -1, right? Even for easy things like this, it's tedious, okay? What's that? I can't hear.
Is it based off the unit circles like we have?
Yeah, basically, yeah. But no matter what you base it off of, it's that, okay, that's 4.5 is somewhere about here. This will be positive again here, right? Now I'm just going to go based on a few of these. Okay. You can do more points in between. They do, okay? Good luck for them, okay? So there's your, at least the beginning, okay? And by the way, you can get software will do this for you much faster than I would. Okay, but just give you a shot. Now, the fact that we have an initial point, this would be good for any initial point of x equals 0, y equal negative 3/2. So x equals 0, that would be here. Y is equal to negative 3/2. That's going to be somewhere awfully close to this point. Whoops, 3/2 would be here. Okay? No, I'm sorry. Yeah, x equals 0, y is equal to negative 3/2. That would be right. It's negative 1.5 is what I had to begin with. Awfully close to here, that point right there. Okay? Now, that's just a point, but you see this curve is going down here and decreasing until it has basically a horizontal asymptote of this, and up here it's okay. It's going like this until it has a horizontal asymptote there. I mean, that looks suspiciously similar in some senses to either a inverse cotangent curve or something like that. It's not, okay? But that's generally the thing. If you had got more points in there, you'd see these are going from 0 to 1, so these are decreasing steadily here, then increasing steadily here from negative 1 back up to 0. So that's basically what you're doing. There's a whole family of them there, but the initial condition picks one point and then find the line that connects on both sides of that point. Generally, qualitatively, that's all we're doing there. Okay. Now, there's a little remark section here. And this is sketching direction field by hand is straightforward, but as you've just seen, very time-consuming. Okay? Before calculators, PCs, software, the method of isoclines was used to facilitate sketching a direction field. Does anyone know what isocline means? Have you ever looked at weather maps and those sort of curve-like closed things that go around certain things? You call them high-pressure areas or low-pressure areas. Those are called, those lines, those curves there, are called isobars. What would that mean?
In other words, you said iso.
And isocline, if you've ever, any of you at all even know what orienteering is? It's a sport, okay? It's a sport that what they give you, they put you out in the woods somewhere. Someone set up a course there, way out in the woods somewhere. They give you a map and a compass and send you out. And you are supposed to complete the course in the order that they indicate, because they have stations at various places indicated on your map, and you have to figure out what it is. So your compass gives you what way to go, and you have a general. Well, the map they give you is a topographic map. Anyone know what a topographic map is? It has those same kind of curves on them. Those are called isoclines. Areas, iso means equal, okay? Isobar is equal barometric pressure. So if you have a high pressure here, and then around it you have isobars decreasing as you go out. If you have a low pressure here, the isobars are increasing as you go out. But those are always the centers of your activity, okay? Well, isocline would be areas of equal elevation. I don't know how they get cline elevation, but those are what they would use. Equal values, basically, okay? That's just a little blurb. You don't really probably need that much. So let's go to 2.1.2, okay? That was all 2.1.1 direction fields. 2.1.2 is now going to be talking about something they call autonomous first-order differential equations. Okay? Now, what in the world does autonomous mean? Can you think of anything that's autonomous? Second? I can't hear. Okay. Probably a little bit similar to that. I think in terms, because I remember this for some reason in terms of biology, you have two types of nervous system, maybe more than two, but one is your autonomous nervous system. In other words, that thing, whether you think about it or not, it's going to happen. That's what keeps your heart beating. That's what keeps your, think. Say again? Involuntary. Yeah, autonomous. Yeah. Automatic. It's going to happen, You can be dead asleep, anything else, your heart keeps beating. That's the autonomous systems, okay? Ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. We just had one. dy dx is equal to sine y. There was no x anywhere in there, okay, except it was the independent variable. That's what you're taking it with respect to. So we'll assume throughout, so here's the generic form of writing an autonomous differential equation. dy dx is equal to f of y. Now, of course, your independent variable could be t, it could be y, it could be z, it could be anything, but whatever your dependent variable is, that's the function that you're dealing with, okay? Now, we'll assume throughout that the function f and 2 and the derivative functions are continuous functions of y on some interval I. If they're not continuous, just hang all this up, okay? So here's another example. dy dx is equal to 1 plus y squared, okay? That's autonomous. No x is in sight except in your derivative, right? Now, tell me something about that one. It's certainly ordinary differential equation, certainly first order. This whole section, the whole chapter is first order. Nonlinear, very good, okay? How about this one? dy dx is equal to 0.2 xy, okay? Is that autonomous? No, you see an x in there, okay? So forget that one, okay? Now, many differential equations encountered in applications are equations that are models of physical laws that do not change over time are autonomous with respect to t. If there's no time variation, they're autonomous. As we've already seen in section 1.3, we did a whole bunch of those. Remember these? dA dt is equal to some constant of a, right? Population densities, population, there's whole sorts of things there. There's no time dependence in that. It just depends on the dependent variable, okay? I can't remember for sure which one this was now, dx dt, but I remember we did it. I think this was the z-spread or something like that. Kx times n plus 1 minus x, okay? As much other stuff is in there, there's no t dependence there, so this is autonomous, okay? You'll run into this quite a bit. Newton's law of cooling and warming, dt, where capital T is temperature and little t is time, is some k times T minus Tm, I believe this book uses. Tm being a constant, your ambient, temperature. The T is your variable. No little t, no time dependence in that. Okay? We had one like this with our brine solution. dA dt is equal to 6 minus 1 over 100A. That's an autonomous. There's no time dependence here. It all depends on your quantity. Okay? Which is surprising. You would think that brine solution would depend on time too, but it's not. Now, let's go to let's say we have those functions, okay, that f of y. The zeros of that function, f of y, or whatever it's a function of only the dependent variable. The zeros are of special importance. They say that a real number c is a critical point. Now, we had that back in Cal 1, right? You had critical points. Is this the same one? Kinda, okay? Critical point of autonomous differential equation 2 if it's a zero of f. Well, yeah, that is the same thing we were saying. Remember, your critical points were, actually there's one more caveat. dy dt is equal to f of y. If you found the zeros for that, those would be where your first derivative is 0, right? And that would be max, mins, or points of inflection. Now, the only little difference here, back then a critical point would also be where the derivative is undefined. We're not counting those as critical points here. We're just using the zero, the horizontal slope critical points, okay? Say that C is a critical point of the autonomous differential equation if it is a zero of F. That is, f of C is equal to 0. Critical point is also called an equilibrium point or a stationary point. In other words, momentarily, maybe just for the moment, there is no change right then, okay? Now, observe that if we substitute the constant function y of x into 2, then both sides of the equation are 0. That means if C is a critical point of 2, then y of x equals C is a constant solution of the autonomous differential equation. Okay? Almost feels like you're going in circles here. That's called the equilibrium solution, and that equilibria are the only constant solutions that make that work. Okay? Now, this may be a dumb example of this, but it is one, we're doing it in my physical science class. If you plotted how high the sun is at noon every day, real noontime, not just noon on the clock, but the highest point the sun reaches every day of the year, you'll see that right now it's getting a little bit higher every day at noon, a little bit higher. Will it keep going higher and higher? No, at some point it doesn't get any higher and starts going down. What do we call that? The highest it's going to be. Does anyone know about when that would be? Second? I couldn't hear. Yeah, that would be the highest point. That where your shadow is going to be the shortest at noon that day of the year. After that, it'll only get longer again. What do we call that day? Actually, it's pretty close to you. Yes, that's it. The solstice, the summer solstice. And what solstice is the sun, sol, stands still, stis. Okay? It stops going up, and after that, it starts going down again. Okay? Then it keeps going down until, and by the way, that's around June 21st. So it's coming up this month, the summer solstice. Then it'll start going down again, and around September 21st or so, we'll have, that has a special name. Say again? No, the winter solstice is December 21st. We're getting there. Then it stops going down and starts going up again. Okay? That's winter solstice. In between there, about September 21st, somewhere in there, is what we call equinox. At that day, you have equal day, equal night. 12 hours sunlight, 12 hours darkness. Up here, you have more sunlight, less darkness. I mean, the nights are getting shorter, the days are getting longer, right? They'll keep going until June 21st, and they'll start reversing. Equinox is, okay. So there's an example of a critical point when it reaches the solstice here or the solstice there. Now, just a little note there. The ancients used to always fear, they watched the sun, and they knew it was getting lower in the sky every day. And they feared, and it was getting colder, right? Every day, not every day, but, pretty much. As the sun got lower and lower, it got colder and colder. And then they feared that some year, sometime or another, the sun may not quit going down and disappear, and they'd freeze to death. That was a superstitious fear and stuff. So, when they saw it start rising again, they threw a party. Okay? Yay, we're going to have the sun another year, And they were so happy, and they celebrated. And that was the origin with a lot of the celebrations that occur around winter solstice. Now, I hope you don't take this negatively, but I think it's been pretty well documented that probably is why the early Christians chose to celebrate the birth of Jesus around December 21st. Okay? Everybody was partying anyway. They got to party for a different reason and got to fit in, because in reality, shepherds probably weren't watching their sheep at night in the middle of winter, okay? That probably didn't happen. They probably had a nice warm area, So the whole story probably means we got the time of year wrong there, but that's probably the reason they chose it, so they could celebrate and party, but they were celebrating something completely different and not getting into trouble for doing it. Okay. All right. Sorry, that probably was a negative. Okay. Let's do example 3 here. Here's a differential equation. Let me erase this one. Oh, no. We have done it again, haven't we? My dumb story. Okay. Rectus. Okay. Homework exercises here. Glad you caught that. I would have kept on trucking. I think you can do any of the odds, either 1 or 3 or both. Those are directional fields. They say use computer software. You can draw out some of these, any of the odds 5 through 11. Okay. And probably stop there because we'll need to do example 3 before 13 makes a lot of sense to you. Or 15 maybe too. Wow. No, I'm sorry. You can do 13 and I think you can do 15. Okay? It's 2.1. That's the place we didn't do an exercise in that for you to see. So we'll stop after 15. 17 is one of the discussion. There is a word there, nullcline. If that's something of interest to you, you can pursue that, but you don't have to do those. So we'll pick up there 2.219 next time. Good deal. Let's see. How do I get out of this?